Hello, welcome to Zig for the Uninitiated. My name is Tyler. Let's get started. Today I want to take some time to talk about Comptime and generics. This is something that's been requested as a topic that some people wanted to see some more of to get some better understanding. And I'd like to give a real use case of where Comptime enables generic programming to see how it's uh, useful and how it works. And yesterday, while I was working on this project for some message pack protocol, I stumbled onto an example that I think is really cool, really fun, and it helps explain how to use comp time programming to do some generic programming. Okay, so before we dive into this code, though, I want to kind of give a background of what I was working on. So yesterday, I was working on this message pack. Not a library, but just some code to help send some message pack data between a process and NeoVim. And as part of it, I needed to implement the int format family spec for message pack. So if you don't know what message pack is, it's a format for transmitting messages between servers or processes, and it has different ways of specifying different types as you transmit that. In fact, it's used a lot for our different RPC protocols because it has its own RPC protocol. And that's what I was using it for. I was using it to trigger certain procedures on NVim or NeoVim, which NeoVim supports an RPC server that uses message pack. That's all aside. The thing that we need to focus on here is this int format family. One of the goals of message pack is to be very compact, meaning that you're not sending a whole lot of data if you don't need it. And in that, because of that, integers can be sent in 1, 2, 3, 5, or 9 bytes, depending on the size of the integer. And what we see here is this positive fixint stores 7-bit positive integers, and this negative fixint stores 5-bit positive integer, 5-bit negative integers, which means that we can use 1 byte to, if we have a small enough number, right? A number between, let's see, negative 64 and I believe that, or no, negative 32, right? Yeah, I believe so. Negative 32 and positive 128, then we could send that in 1 byte. However, if we need to store bigger values, then we have to send just a whole byte preceded with a little header here, the 0xcc, which heads it off saying this is an 8-byte integer. And the same thing with this one. This is 0xcd is a header byte that just says the thing to follow, the next 2 bytes, basically. There's a 16-bit integer, and then so on and so forth, 32-bit integers, 64-bit integers, and it starts over again for your signed integers. So these are unsigned and these are signed, which means that there are in total 10 different ways that you can send numbers, though technically this 1 bit is kind of the same way. But anyway, 10 different ways that you can send numbers across the wire. Okay, let's take a look at our write int function. Now, the first parameter of the write int function is this writer, and we don't really need to worry about it. It's just used to write out the integer value into a buffer that is then used in another function. This create request function hands us that writer so you can write into the buffer. Not pertinent to what we're talking about here. First, really pertinent parameter is this parameter type t. Now, in other languages, you'll be used to seeing something like this. You'd see, say, if this is Rust, write int, and it's been a long time since I programmed in Rust, so I don't remember if I've got the syntax quite right here, but I think it would be write int t, which means this, you'd have these angled brackets, which would say, hey, this integer function is generic over type t. So then you wouldn't need something like this. You just have, hey, write int type t, and then you'd use that type t in your signature. However, in Zig, we don't have syntax like that. Instead, types are just first class. So you can use them as types and parameters, or you can use them as values for parameters. So we just say we can just say t, this right int function takes a parameter t, which is of type, which means it's a type. And then we can then use that parameter inside the function. We could say int is of type t. And this might seem really weird at first, but really it's no different than the angle bracket syntax. I mean, it is different, but it's no different. You'd have to declare your type that you're parameterizing over there. Instead of declaring there, we're just declaring it here. And because we declare it here, and because types are first class at compile time, we're able to use that parameter inside the function. Not just here where we say int is of type t, we say, okay, I want to get the type info. Here, my standard is just called type info ti. I say, hey, give me the type info, and type info is just a struct. We go to the definition, it's not a struct, sorry, it's a union. It's a tagged union with different values. In fact, each of these are, most of these are different structs that contain other information that we want to know. Now, at Comptime, this is a kind of on the side about Comptime. I want to assert that the type that's passed in here is an integer, meaning I want to make sure that whoever is writing with this function only ever calls it with an integer type. And so I can do that by using this Comptime, and I assert that the type info is integer. And the reason why I can do it at Comptime is because types are always known at Comptime. They're not known at runtime. And so this type info is Comptime knowable. And so I'm able to take that type info at Comptime and do some logic on it. So I'm asserting that this is an integer. This has nothing to do, this isn't necessary for it to be generic. It's just a little safety check for me to make sure that when I write this, if I ever use this, I don't accidentally pass some other value to it. I also make sure that the value, the type that's being passed, is only 64 bits in width, because message packs only supports integers up to 64 bits. And I can check that because int is, if I go to the definition of what this int struct is, it has two fields. It has assignedness, which tells us if the integer is signed or unsigned, and as a bits value, which tells us how many bits are in that integer. Now, I can take that signedness, right? And I can take that bits, and I can take those information. So I just aliasing those values so I can reference them later. Gotta let's unfold all this. Oh my goodness. I didn't realize how much I folded. Okay. And I can see some things. First, I switch on how many bits there are. And 0. I say 0 is Comptime unreachable. Not because I've checked to make sure I'll never pass 0, but to me, 0 is meaningless. And that if a programmer gives us a U0 and I0, there must be an error. And so I want it to not compile. That Comptime unreachable means that if the code is being compiled and ever goes down this path, meaning it's hit a 0, then something wrong has happened. Then from 1 to 5, I send it. If its values are between 1 and 5, I check to see if it's signed or unsigned, and I send it into negative or positive fixed int, depending on what it is. And if it's 6 to 7, I do the same thing, except for that if it's signed, I send it to the generic write in bit int. And we'll talk about what that one does. It's another generic function. Otherwise, I send it to the write positive fixed int function. This function is not generic. The write positive and write negative fixed int functions are not generic. They are just regular functions that take an integer and write it out. But this write in bit int function is generic. It's another generic function. And what it does is, well, we'll get to it, but the reason why is because if you look at this, the pattern here is similar. Between, if you get a unsigned or assigned 8-bit integer, you just write that integer out in big Indian with some leading header byte. So really, I want to write, what is that, 1, 2, 8 different functions that all do exactly the same thing, but are different based off of the type of the value. And so I needed to have it be generic because it needs to be dispatched based off of the type that's being passed in. Found a bug. There we go. So, oh, and I need to make sure to declare that that is Comptime. Okay, there we go. Sorry, found a bug, and so I needed to make sure that I fix it. Catch unreachable. Okay. So let's take a look at the write in bits function. The write in bit int function takes in, once again, a writer, but now it takes in the signedness and the bits. And there's a reason why I did it this way, because I need those values anyways, as Comptime parameters, meaning that this value is going to be, needs to be known at Comptime. The reason why I have to declare these as Comptime and I didn't have to declare T up here as Comptime is because types are always only known at Comptime. So I could do Comptime there, but it really doesn't add any information, and any other information. It's not required. It is required for this write, where is it? It is required for signedness and bits because those aren't inherently Comptime values. Info.signedness is just this flag. This is a runtime knowable type, or a type that can be known at runtime. And so I have to make sure that I declare that this value has to be known at Comptime. And part of the reason why is because I use it with this int function, which is new in 0.16, this int built in. In 0.16, the type, there used to be a type built in, used to build any types. And those are all replaced by separate built-ins, which allow you to build specific types. And it's actually a little nicer interface because here I know I want to build an integer, and I already have the signedness and the bits. And so it just tells me that this integer has to be of the type whatever this signedness is and whatever the bits are. And then all I do is I take in, I find out what the header byte is, and I do this at Comptime. I take the Comptime value and I find the base. If you look at this, the base header value is CC, and then just goes up in hex, right? CC, CD, CE, CF, D0, D1, D2, D3. So it's a span of 8 numbers. And so to figure out which value is, I just check if it's signed, then I add 4 to it. This is just a fancy way of saying add 4 if the value is signed. If it's unsigned, add 0. In fact, I should probably do it like this to make it more obvious what's happening. Okay, the bit adjustment is just taking the logarithm of the bits divided by 8. So just say the natural log bits divided by 8 tells us how many steps we are. Are we at are we at 1 byte, 2 byte, 4 byte, or 8 byte sized integers? And that's because if I go up to here, this bit width function that I added in right here takes whatever the bits are, right? Remember, the bits are the size of this integer, and it just converts it into the next highest multiple of 2. Unless it's already multiple 2, then it keeps it at that multiple 2. It's just an alias for the ceil power of 2 function. All right, so back to where we were working at here, and then we just add it, and that adds together, gives us the header byte, and then we just write it out. And so this is a really nice way to write essentially 9 different functions or 10 different functions, and I only wrote 1, 2, 3, 4 functions. right? This one that does the dispatch to the right version, and this one that handles the case of a negative fixant, handles the case of the positive fixant, and the one that handles all the other cases. So I can prove that this is indeed generic by writing this function. So if I take the readelf command and I do -s for symbols, -- wide, make it wide, and I do a.out, which I have prepared, and I grep for message pack dot, was it? Write in bits, write in bit int, you'll see that I get this list of integers here. I get 1, 2, 3, 4, 5, 6, 7, 8 different functions. And that will correspond to the fact that I've, in my test cases, have written 1, 2, 3, 4, 5, 6, 7, 8 different functions that use different types. And so these types are all covered here. Furthermore, if I do write int, you'll see that there are 10 different functions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 functions here that use the write int. Now you can see that they use this anon because when the function is created by the compiler, it has to add in this anon and then a number referencing the type. So I can't tell you exactly what types are which. However, I can tell you that these different types, or these different numbers, reference the fact that this is a function made for a specific type, and the compiler keeps track of all that. And that's kind of it. That's all I wanted to show, but hopefully that gives an example of how you can use Comptime to write functions that are generic, and how to understand maybe the syntax of it. Generics in other languages have special syntax. Zig doesn't have that. It just uses the regular parameterization of a function using a type as a value. That's probably the key takeaway. So that's it for the video. I do want to announce, though, at the end of the video, if you want to stick around, that I will be speaking in October, on October 6th, at the Software You Can Love conference in Vancouver, Canada. I'll be one of the Software You Can Love speakers. So that'll be, like I said, on October 6th. The whole conference goes from October 3rd to October 6th. It looks to be a great fun conference. Tickets are still on early bird pricing for, I think, the next 2 days. So if you want to get tickets, now's the time to get it. And what's nice is you don't have to buy a ticket for every day, because it can get, like, I understand this is pretty expensive. Maybe if your work would support you to go there, that's great. But if you want to make it to one of the system talks, the SQL talks, now is a good time to buy your tickets. Thanks for watching. Happy programming.